Hello friends, once again I welcome you all for my class on experimental physics. Friend, this year you have to study a resonance pendulum. That means you have to study the phenomena of mechanical resonance, and you will see that this mechanical resonance you can study with the help of compound pendulum. So in order to understand the physics of resonance pendulum, you first understand what is a compound pendulum. As you know that in first year BSc you have studied the bar pendulum, and using that bar pendulum you have calculated acceleration due to the gravity, and at your higher secondary level you have studied the simple pendulum and you have also calculated acceleration due to the gravity. Today we don't want to calculate the value of acceleration due to the gravity, but we want to study the phenomena of resonance, and we want to find out the damping coefficient of damping. So that we will see, but to understand and to perform the experiment of a resonance pendulum, you should know what is a compound pendulum and how it differs from the simple pendulum. You people already know about the simple pendulum. Basically, a simple pendulum is a body of mass m suspended by a string from the fixed support. You see that is a body of mass m, right? This is you can see a sphere of mass m, which is suspended by a string of length L from uh, uh, which is uh, which is from the fixed support or rigid support, you can say here, and the length of the string is suppose is capital L. And you can see that in case of a simple pendulum, there is no distribution of mass, because the length, the mass of the string is very negligible, and the entire mass of the pendulum is concentrated at a given point here. So in case of a simple pendulum, you know that the periodic time of a simple pendulum is depending upon only the length of the pendulum, and we know that the relation of a simple pendulum for a periodic time of a simple pendulum is equal to 2 pi square root of L by G, where L is the length of the pendulum and G is acceleration due to the gravity. And you know that a compound pendulum, basically it is a rigid body of either a regular shape or an irregular shape, which is capable of oscillating in a vertical plane about an axis which is passing through it. So once again, I would like to define a definition of a compound pendulum. Uh, any rigid body, I would say, either you have a regular shape or an irregular shape, which is capable of oscillating in a vertical plane about an horizontal axis passing through the rigid body, is considered as a compound pendulum. So here you can see there is a figure which I have mentioned. You have a rigid body, and you can see that rigid body is suspended from the point P, and you can imagine there is an horizontal axis passing through the point P. So I would say that your rigid body is pivoted at point with respect to the point P. This is the horizontal axis which is passing through the rigid body. And now if you give a small angular displacement to your body, that is to the rigid body, then this body is capable of oscillating in a vertical plane. And if the angular displacement is very small, then the amplitude of oscillations of the rigid body is very small. And if the amplitude of oscillation is very small, then these oscillations are treated as simple harmonic oscillations. So it will perform a simple harmonic motion. So here you can see that this irregular rigid body is treated as a compound pendulum. As I said that there is either you have a regular body or you have an irregular body. In case of a regular body, you may imagine your bar pendulum, which you people have used at first year BSc to understand the concept of acceleration due to the gravity. So here you can see there is a metallic bar, and you can see that, and you see that there is a distribution of mass along the bar of the pendulum. Here you see in case of a simple pendulum, there is no distribution of mass. Mass is concentrated at a particular point in a metallic sphere. That is the bob of the pendulum. And here you see there is a mass is not concentrated at a particular point in a compound pendulum. There is a distribution of mass along the bar of the pendulum, and because of that you will have a point where the entire mass is concentrated. That is a center of, that is a, I would consider a center of gravity, or let us say center of mass, which we can locate on the bar pendulum. So bar pendulum is basically a compound pendulum, because you see here the bar pendulum, it is pivoted at, suppose this is the point P, right? Let us say this is the point P, then you may imagine there is an axis which is, there is a horizontal axis passing through the point P, and your bar pendulum is suspended with respect to this horizontal axis, right? And if you give a small oscillations, then your bar pendulum will oscillate, and these oscillations are very small, and you may treat your bar pendulum as a compound pendulum. And this is the as pendulum which you have used at first year BSc. And you can see that the periodic time of the compound pendulum is given by this expression 2 pi square root of L square plus K0 square divided by GL, where you know this small l is a distance between the point of suspension to the center of mass of the pendulum. So this is the distance L, you please remember, and as you can find it out. So please remember L is the point of suspension. Point of suspension is the point through which your horizontal axis is passing through the compound pendulum, I would say, through the body, through the rigid body, through the bar pendulum. And you have a center of mass, right? That is the center of gravity, I would say. And you measure the distance between the center of mass to the pivot. This distance is known as L. And K0, which I write down, which you are familiar, that is known as the radius of gyration of a pendulum about center of mass. So K0 you can calculate using the formula which you people have already used. So you can see that the L square you can calculate, K0 you can calculate, and you can find out the periodic time of a compound pendulum when it is oscillating in a vertical plane with a small amplitude. In case of a simple pendulum, you remember its periodic time is given by 2 pi into square root of L over G, where L is the length of the simple pendulum and G is the acceleration due to the gravity, which you people have already calculated in your previous classes. Here, the periodic time of a simple pendulum is only depending upon the length of the pendulum. It does not depend upon the mass of the spherical bob. Here you have a point mass, and here you have, in case of a compound pendulum, you don't have a point mass. The mass is distributed. There is a distribution of mass along the length of the pendulum, and that's the difference between the simple pendulum and compound pendulum here. And here, using the compound pendulum, we want to understand the phenomena of resonance here. So now, first of all, look at this equation. This equation is quadratic in nature. If you find the relation between these, because there is a relation of t and L square. So this is a quadratic equation. So if you solve this quadratic equation, for a given value of t, for any given periodic time t, you get two different values of L. That means you get the value of L is equal to L1 and you get L is equal to L2. So you see here I have mentioned L here. So if you consider this point, you see if you consider the point P, if you uh, basically suspend your pendulum with respect to P, and if you find a periodic time of the pendulum, then you will get the distance between the point P and G is equal to L1. But since there are two possible values of L1 and L2, that means there must be some another point of suspension on the axis on the other side of a center of gravity. That means there should be some a point O, and so if there is another point on the other side of the center of gravity, then if you suspend your pendulum with respect to the point O, that means I mean to say that if you invert the pendulum and suspend your pendulum with respect to the horizontal axis passing through the point O, and if you measure its periodic time, so once again you will get that periodic time t is equal to the same periodic time which you have calculated with respect to the point t. So with respect to the point P. So the distance of the point of suspension O, which you are getting on the other side of G, to G, that is distance OG, if you measure the distance OG, once again that distance will be considered as now L2. So you have got a 2 point of suspension with respect to the point G. So if you suspend your pendulum with respect to the point P, or if you suspend your pendulum with respect to point O, both the cases you get the periodic time T1 is equal to T2 is equal to T. So you get the same periodic time. So you get length L1 and you get length L2. On this principle, you have to also study another pendulum, and this pendulum is also a compound pendulum, and it is basically known as Scatter's pendulum that you will study in third year BSc Physics, and you will find out the acceleration due to the gravity using the concept of Scatter's pendulum. So now once you understand that there are 2 points of suspension you get on other side of a center of gravity, this is an invertible pendulum. You can invert the pendulum. You can suspend the pendulum about the knife edge, about the point P. So you can have a knife edge and you can suspend your pendulum with respect to the point P. So you can imagine a horizontal axis passing through the point P and you can find its periodic time. Once again, you invert the pendulum and you can suspend your pendulum with respect to point O, and again you imagine a horizontal axis passing through the point O and you measure the periodic time. In both the cases the periodic time is same. So and once you know this, so you can write this expression here and you can see that this expression, I'm sorry, this expression you can write. So I get uh, with respect to the point P. So you see there are 2 points of suspension which we are getting with respect to point P and with respect to point O. So I write down with respect to point P, I measure the length L1, and with respect to point O, I measure the length L2. So you have the length G to P is L1 and you measure the length from G to O is L2. Both the cases the periodic time is same. So I can write this formula in this case T equal to 2 pi. This is the periodic time of a compound pendulum. For L1 you write down here L1, so L1, and for L2 you write L is equal to L2. Both the periodic times are same. If you compare both this expression, because the periodic time is same, so you get K0 square is equal to L1 and L2. That K0 is the radius of gyration of a pendulum about its center of mass. And you can see that if you put K0 square is L1 L2, you get P equal to 2 pi under root of L1 plus L2 into L into G. And if you solve this, L1 plus L2 is known as capital L. and capital L is called the length of the equivalent simple pendulum. Please remember, capital L is known as the length of equivalent simple pendulum, as the period of oscillation is same that of a simple pendulum, right? So now we will, this is basically the expression of a simple pendulum, 2 by root L upon G. And this is the concept which we will use in this experiment, right? And we want to study the phenomena of mechanical resonance. So this is an experiment which you people have to perform. You have to perform a physical pendulum, that is a compound pendulum, and you have to study the resonance here. So you see, let me show you the physical arrangement of your experiment. This is the experiment which you people have to perform. Look at this. This is the picture I would like to show. I will also show you the video film. I will also explain you the procedure, and I will also explain the concept which we are using here. And look at the experimental arrangement here. Look at that, you have a long metallic bar where you have the uh, there are various holes you can see, which are symmetrically placed. So this metallic bar which you can see here is basically a bar pendulum, and this is the bar pendulum you have already used. So you can have your point of suspension of a bar pendulum, right? So look at the figure here. Here, this is the knife edge you can see. So I suspend the bar pendulum about the knife edge. So here you may imagine that there is a horizontal axis which is passing through the point of suspension. So this is basically a point of suspension of your bar pendulum, and your bar pendulum can oscillate in the vertical plane. So this is it can oscillate in the vertical plane. So you can see the picture here. So this is here, this is the bar pendulum, this is the end of the bar pendulum. If you give a small displacement, your bar pendulum will oscillate, and you have a oscillation in a vertical plane. The oscillations should be very small. So if the oscillations are very small, if amplitudes are very small, then these oscillations are treated as a simple harmonic oscillations, and it will perform a simple harmonic motion. Now we have made an arrangement. There is a hook, there you can see there is a hook which we have connected here. So you may imagine there is an horizontal axis here. This hook is working as a horizontal axis, and here this is there is the end of this hook. We have attached a simple pendulum of length L and mass M. So you can, if you look at very carefully this figure, if you can see there is a string, you can see there's if the quality of picture is not good, but I will show you the video film where the string is visible. So I have attached a string of length L, uh, and this string of length L is attached with a mass M. This is basically a small pen of mass M. This pen is of the order of 2 gram. Please note down. Okay, and this pen is attached with the string, and the string is fixed. There is a fixed support here, because this fixed support is given by this horizontal axis which you have, that is the hook which we say, right? So you can have your simple pendulum. Basically you have a simple pendulum of length L which is attached with the bar pendulum, and you can see that behind the simple pendulum, behind it you see behind the simple pendulum there is a horizontal scale which we have placed, right? And this horizontal scale is calibrated, and you can see the scale. Right now the quality of picture is not good, but when you will see the video film, you can see the scale on the you can see the scale on the scale here. Okay, fine. Now, what you people have to do in this experiment is you have to oscillate uh, the say a bar pendulum. So when you oscillate the bar pendulum, right? So bar pendulum will start oscillating, and these oscillating bar pendulum will activate the simple pendulum. It will drive the simple pendulum because it will transfer energy to the simple pendulum. Your resonance pendulum, the compound pendulum, transfers energy to the simple pendulum. There is a transformation of energy. And when energy is transferring, your simple pendulum will also start oscillating. So along with the harmonic motion of a bar pendulum, you will see that this simple pendulum of length L will also oscillate. And this oscillation you can see because there is a scale behind the screen. So when your oscillator is oscillating, right, you will see that there is also a oscillations of a simple pendulum. As the energy is transferring, you will see that the amplitude of a simple oscillator gradually increases, and it reaches to maxima, and you will have a maximum amplitude for a certain value of length L of a simple pendulum. So you please remember, how do you measure the length of the pendulum? You can see that this is the point of suspension of a simple pendulum. So if you measure the distance from point of suspension to the point mass, I would say this is the point mass. This distance, if you measure from this point, I'm sorry, if you measure this distance, uh, uh, distance from this point, you take a scale and you measure the center of the pendulum, right? And because mass is concentrated, you measure the length of the pendulum. You can change the length of the pendulum because this you have the length of the string is variable, and you can wound. I'm sorry. You can wind the thread on this axis. I'm sorry. You can wind the thread on this axis, and you can change the length of the string. So the length of the simple pendulum is variable. You can change the length. You can keep the desired length. Suppose you want to keep L is equal to L1. You can change the length because the length is variable. You can wind the thread along this horizontal axis, along the fixed axis, and you can vary the length. And once you can vary the length, you can have this experiment for various length of simple pendulum. See, now we want to understand a very important concept, that when the periodic time of the bar pendulum is equal to the periodic time of the simple pendulum, when the periodic time of both the pendulums becomes equal, then the amplitude of the simple pendulum will be maximum, which you can observe on the scale which is attached behind the simple pendulum, which you can see here. This is known as phenomena of resonance. So in this experiment, we have to find out the length of the simple pendulum for which the amplitude is maximum. You can measure the amplitude on the scale. Basically, you see this experimental arrangement, you will be given a telescope. You have to focus the telescope, and you have to focus the thread. Once you focus the thread of the simple pendulum, you can see there is a scale behind the thread. The scale also will be visible. You focus the telescope very carefully so you can see the thread along with the scale. And now if you give a small oscillation, then within the view of the telescope, within the, you see, you have a telescope eyepiece. So within the scale of the eyepiece, within the range of the eyepiece scale, you can observe the oscillating simple pendulum, and you can find out the amplitude of a simple, I would say that simple pendulum. So when your compound pendulum is driving the simple pendulum, you see basically when energy is transferred, you will see that the amplitude is gradually increases. So when you look at through the telescope, you will see that the amplitude of simple pendulum is slowly increases, reaches to maxima, and again it will decrease. So you have to find out the maximum amplitude, and you have to note down the maximum amplitude of the simple pendulum on both the sides of the both the sides of a point of equilibrium. Okay. So this experiment I would like to show you. I would like to show you the video. First of all, I would let me explain what is the resonance. I have explained you the phenomena of resonance. So at the time of resonance, you see the periodic time of the bar pendulum is always equal to the periodic time of a simple pendulum. Now, periodic time of a simple pendulum is equal to 2 pi square root of L over G. So the periodic time of simple pendulum is equal to the periodic time of bar pendulum. So using this formula, you can find out the length of the pendulum. You see, so what I will do first in this case, you when you start the experiment, it is better to find out the resonance length. So the resonance length of the pendulum is basically considered as the length at which the periodic time of the simple pendulum is equal to the periodic time of the bar pendulum. So I know that expression. So you see, I can show you a very simple way. This expression, look at this expression which I have used. T equal to 2 pi root L over G. So if I solve this formula and if I make the order L0, so L0 is equal to GT square over 4 pi square, that is in terms of centimeter, where T is a periodic time. And this periodic time T is a periodic time of a simple pendulum. And when a periodic time of a bar pendulum is equal to the simple pendulum, then you have a maximum amplitude. So you have to first case, you find out the periodic time of the bar pendulum. So you see this you can see that free end of the oscillator of the bar pendulum. Give a small oscillation and measure the time for let us say 20 oscillations or a 25 oscillations or a 30 oscillations or a 50 oscillations. Generally we measure time for 25 oscillations. So you measure time for 25 oscillations of the bar pendulum, which we have already performed this experiment at first year BSc, and you know how to measure the periodic time of a bar pendulum. So you basically activate the bar pendulum, give a small displacement so that the amplitude of oscillation becomes small, and measure the time required for 25 oscillations. Then you measure the periodic time, this T. That will be the periodic time of simple pendulum for the resonance. So I use this formula, and you look at this formula, and which I use this formula, and you can see that T is equal to suppose whatever the T you calculate, you substitute the value and find out the value of L0. So this is known as the length of the simple pendulum. This is the resonance length of the simple pendulum. This is the length. So if you adjust this length, L0, so this is known as the resonance length. So you, when you measure the distance between the point mass M uh, to the axis of suspension, this is the point of suspension, the fixed point. So if you measure this, if you keep this distance is L0, distance between the point mass to the point of suspension of a simple pendulum is L0. And if you oscillate your bar pendulum, then you will see that in that case, the amplitude of your simple pendulum will be maximum. So in this experiment, you have to perform uh, two parts. The first part is to find the resonance length. You have to estimate the resonance length, I would say. So use that expression which I have mentioned. You see this expression I have already mentioned here, that this expression you have to use it. Using this expression, find out L0. So the first part is over. Second part, when you start with the second part of the experiment, once you know the value of L0, then we can understand that this is the resonance length. So you take a different values of the length of the pendulum. So you may take, suppose L0 is suppose 60 centimeter. Then you take first of all L0 minus 5 centimeter. Okay, so you take L0 minus 5. So you adjust the length of simple pendulum is L0 minus 5. So this length, the point of suspension to the point mass which is suspended here, the mass of the pendulum is 2 gram. So you see, you keep this distance is L0 minus 5 centimeter. So if it is L0 is 60, so 60 minus 5 is 55. So you keep this distance is equal to 55 centimeter and perform the experiment. And you perform the experiment, that means you oscillate the bar pendulum, and bar pendulum will activate the simple pendulum because of the forced oscillations, and you will have oscillation of simple pendulum. So the bar pendulum will drive the simple pendulum, and when energy is transferring, the amplitude of simple pendulum is gradually increases. So when you look through your telescope eyepiece, you will see the amplitude of the simple pendulum is gradually increases. You have to note down the maximum amplitude on both the side of your point of equilibrium, right? On both the sides of point of equilibrium, and note down your result for L0 for the length L0 minus 5 centimeter. Then you take the another length L0 minus 4 centimeter, L0 minus 3 centimeter, L0 minus 2 centimeter. Then you take L0 also. And when you take L0, you will see that the amplitude will be maximum because it is a resonance length. Then again you gradually increase the length by step size 1. You take L0 plus 1 centimeter, L0 plus 2 centimeter, L0 plus 3 centimeter. And every time you note down the maximum amplitude on both the side, that means both the ends of the local oscillator. I mean, the oscillator is your simple pendulum here. And you see that this expression, I will show you the table where you can see this experiment, and you see this part. So let us see, this is the first estimation, then we calculated the periodic time. And once you calculate the periodic time, and now we will go for uh, the second part, you see. And you see, I have taken several observations. I keep the length 56. I measure the maximum amplitude on left hand side, on the right hand side, because you see you have a simple oscillator. So you have a two extreme end, right? And you have a point of equilibrium, correct? So when you have a point of equilibrium, you measure the amplitude on the right hand side, and you measure the amplitude on the left hand side, and you find out the A dash using this formula, A1 dash minus A2 divided by 2, and you find out the maximum amplitude of a simple pendulum is A dash over L into L is basically a length. This is the L is the length of the pendulum, and this capital L, I will show you, this is basically the length which you have to measure from the hook. This is the hook, you see, this is the point of suspension of pendulum. And when you measure the length between the point of suspension to the center of the scale, this is the scale here. So if you measure the distance between the hook to the center of the scale, the vertical distance, this is known as capital L. So I'm talking about the distance between the hook to the scale, center of the scale. You measure the vertical distance, and when you measure this distance, that is a capital L, which you can measure. And this distance is also, I have measured this distance, so you can use this distance here. and you can see this expression, and you can find out your expression and find out the maximum amplitude. Here I have given this length of hook to the scale is 36 centimeter. The reading is I have measured. You please take this observation. And because of the pandemic, you cannot go to the laboratory, but at least you have a feelings to perform the experiments, and you can do this calculation at your residence to have a feeling of resonance. So you take these results which I have taken. The length of pendulum are different. I have taken 56, 58, 60, 63, and 64. Generally, my resonance length is of nearly of the order of 59 to 60 centimeter that you can verify. And now you plot the graph of amplitude, which you see this. This is the amplitude which you have calculated here, and you plot a graph of amplitude versus the length of the simple pendulum, and you can see that the amplitude increases, reaches to maxima, and again the amplitude is decreases. You find out the length at which the amplitude is maximum. So this is the point of resonance. This is the point where the periodic time of a simple pendulum is equal to the periodic time of a bar pendulum. And at this is the point where you see the maximum energy is transferred. And this is the point of resonance. And here, this is the length of the pendulum, which you can find out from the graph, and this length which you can find out from the graph, and the length which you have calculated using the formula are of the same order. There should be a good agreement between the estimation of L0 which you have calculated and the value of L0 which you have obtained from the experimental observation. This is your observations, and once you use this observation, if you plot the nature of the graph, you will find out the answer and you compare this L0. I think before we go for the third part, I would like to show you a video film, and let us see the bar pendulum and compound pendulum in action, and then you will have a real feelings about the experiment. So let me show you that how your pendulum is oscillating in a vertical plane, and when you have small oscillations, you see how your bar pendulum is driving the simple pendulum, and you see because of these forced oscillations, you will see how your local, I mean your simple pendulum is oscillating in a vertical plane, and you will have a phenomena of resonance also, which you can realize when you see the video film. So let me share the file. So give me 1 minute. I will stop sharing this file and I will show you the video film, and which you will understand the meaning of this. So now let me show you another PowerPoint presentation, which will demonstrate the working of your experiment, the experimental setup. So now, first of all, let us see the schematic diagram of this. You see, this is the picture which you people have to do. You see, you have a telescope which will be given to you, and you have to focus the telescope, and you have to focus the telescope, and you have to focus the thread. And once you focus the thread, the scale will be automatically focused, and you see the amplitude of oscillation is very small, so you can see that local oscillation of your simple pendulum will be visible through the telescope, and the scale is already visible. So once your oscillator is oscillating, the amplitude of oscillation increases that you can notice through the telescope, and you can also notice the maximum amplitude of your oscillator, that is the simple pendulum, and you can note down because this is the focusing is proper. You can read the scale, or you can read the scale, and you can note down that observations also. And now you look at your video film, which I would like to show you, and this film which will show you that. Let me show you this film. Look at this. This is the experimental arrangement. You can see there is a bar pendulum, and bar pendulum is attached with the simple pendulum. You can see there is a pen of mass 2 gram which is attached with the bar pendulum, and this is the point of suspension of the bar pendulum, and this is the hook, and which is basically a horizontal hook, and with this hook we have suspended a simple pendulum of mass m, and you can see this is the free end of the bar pendulum, and you can give the oscillation on the free side. So you say I'm giving a small oscillation here, give a small angular displacement, and you see the amplitude is very small, and because of this oscillation, you see this force, there will be a force oscillations here, and you can see your simple pendulum is start now it also oscillating, and if you see very carefully that the amplitude of the simple pendulum is gradually increasing. You can see here the scale here behind the thread there is a scale, and this scale you can focus with the telescope and you can note down the amplitude. You see this is the right hand side, this is the left hand side of amplitude. You can measure this amplitude. You can see here this is the knife edge through which your pendulum is oscillating, and you see this is the way you can take your observation. And once again I would like to show you, you see these observations, look at that field very carefully. This is the pendulum here, and this is the pan. So inside this pan you can put various masses to apply the tension along the string. You can see this is the pen of mass 2 gram, but suppose if I keep 2 gram more, then the additional mass will be 2 gram plus 2 mass of the pendulum plus mass, the additional mass will be 4 gram. So you can change the mass also here. So that is the third part which we want to study here. Look at the film very carefully. This is the bar pendulum, and now you give an oscillations to the bar pendulum. These oscillations will drive the simple pendulum. Because of that, your simple pendulum will oscillate. So you can see your simple pendulum is oscillating right with respect to the fixed point which is attached to the hook, and you can see that there is a scale behind the thread, so you can note down the amplitude of the simple pendulum. You see very carefully, but you have to see through the telescope is given to you, and you have to note down the maximum amplitude on the right hand side as well as on the left hand side. That is the two extreme points of the simple pendulum, which is and then you have to do calculations to find out the resonance length. Well, you can see now, we let us go to the third part of the of your experiment. So I will see that to see the third part of the experiment is to find the damping coefficient, right? So to find the damping coefficient, dear friend, what you people have to do is, now you keep the length of the pendulum fixed. You don't change the length of the pendulum. Now you keep the length of the pendulum, which should be of the order of less than, it should be slightly less than the resonance length. So in the third part of this experiment, you take the length of the simple pendulum, and that length, let us take the length is slightly less than L0. If L0 is 60, you may consider you take the length, let us say the length of the pendulum is around 58 or 57 that you can take. So it should be close to L0 but less than L0 that you should take. Please note down. So you keep that length and you fix the length, and now this is the pen. In this pen you can put different mass. So you have kept the length of the pendulum is constant. It is L, not L0, where L is less than L0. And you keep a different mass. Suppose I put mass M1, and then you oscillate the pendulum and find out the maximum amplitude on both the cases. That is on both the sides, right hand side and left hand side. Then you change the mass M2, you put mass M3, and every time you perform the experiment as you have performed in the experiment in the previous part, and you see, you note down your observations. You see these are the observation which I have taken. You see this is the third part. Look at the third part. So you see the mass in the pan. M1 is the mass of the pan, that is a 2 gram, which is already constant. and now I am again adding 2 grams. So total mass will be 4 grams. So 2 plus 2 is 4 grams. So you please note down here. Then I write down 4 grams. So 4 plus 2 will be 6 grams. Then I'm keeping 5 grams. So 5 plus 2 is 7 grams. And I'm keeping 7 grams. So total mass will be is equal to 9 grams. So this is, I'm taking M2. This is M2 is 2 gram. Then M2 is 4 gram. Then M2 is 5 gram. And then M2 is 7 gram. So in each case, your mass will be now, it will be 4, it will be 6, it will be 7, it will be 9 grams. So you can find 1 upon m square. Please note down. If you know m, you can find 1 upon m. That is, the unit will be 1 upon gram square. Then your observation of maximum amplitude, which I already mentioned how to take the maximum amplitude on left hand side and right hand side, that is a1 dash, a2 dash. Find a dash is equal to a1 dash minus a2 dash divided by 2. Find amplitude of a simple pendulum is equal to a dash over L. You know the length from hook to the scale, that is already measured, which is 36 centimeter. A dash you know, and this is the length which you can consider is equal to slightly less than L0, and find out 1 upon a square. So this you, because you see this for a compound pendulum, there is a relation of amplitude versus amplitude versus the mass which you are keeping in the pendulum. And you see this relation is this is the relation which I mentioned here. The amplitude of a simple pendulum is given by this. So 1 upon a square is equal to L0 minus L divided by L0 whole square, you see, into 1 upon a square, where 1 upon a is some constant, so 1 upon a square plus r square, L square. G is, you know, acceleration due to the gravity. L0 is a resonance length. A is a constant, that is a square into 1 upon a, 1 upon m square, where m is the mass of the simple pendulum that we have already taken. You see, you have your simple pendulum of mass m, which is suspended uh, by a string through a rigid support. So this is your m1 plus m2. So your amplitude of a simple pendulum, you see this amplitude of the pendulum, which is related, the derivation, I will not derive this derivation, is given in certain textbooks. Of course, you can refer several textbook of physics. I would like to suggest the book, a textbook of advanced practical physics by Samir Ghosh, and it is a publisher of Central Book Agency. Once again, I'm repeating, a textbook of advanced practical physics by Samir Kumar Ghosh, Ghosh. The publisher is New Central Book Agency, where the derivation is given. So I request you to go through the derivation part, and you see this amplitude of the simple pendulum, in our case, is related to 1 upon a square is L0 minus L upon L0 whole square, 1 upon a square, R square L square G L0 a square into 1 upon m square, where R is the damping coefficient. And damping coefficient is basically a frictional force per unit velocity. And its unit is dyne second per centimeter, or you may write gram per second. So please remember, Rs is the damping coefficient. R is the damping coefficient, and which we are interested to calculate in this experiment. You see, your amplitude is a dying. You say once again. You see, so we want to study the decay, that how amplitude is decaying, and you see that amplitude of a simple pendulum is given by 1 upon a square, and this is L0 minus L upon L0 whole square, 1 upon a square plus R square L square upon G L0 a square 1 upon m square. Okay, fine. And this when you plot this graph, so this equation is really similar to y equal to mx plus c. So this is your y. Y is equal to m. This is your m. X plus c, which is the variable. Y is this is the one variable y. This is another variable x. So if you plot a graph of y versus x, which is your y? 1 upon a square. Which is your x? 1 upon m square. So if you plot a graph of 1 upon a square versus 1 upon m square, you will get the slope of the graph. Slope of the graph, this is the slope of the graph, mx. So slope of the graph is r square l square over g l0 a square. So this is the slope of the graph. So if you plot a graph of 1 upon a square versus 1 upon m square, the nature of the graph is this, and you get an intercept on the y-axis. And this intercept on the y-axis is given as c, y equal to mx plus c. So this is your intercept. This intercept is I0 minus I divided by I0 whole square into 1 upon a square. So when you perform the experiment, you do the calculation, plot a graph of 1 upon a square versus y versus x. So you see this is your y. Y is 1 upon a square, right? And your x is 1 upon m square. So if you plot a graph of 1 upon y is equal to mx plus c. This is your x. So if you plot a graph of 1 upon a square versus 1 upon m square, so if you see this graph, this is 1 upon a square, this is 1 upon m square on x-axis. You plot the graph, you measure the intercept, you measure the slope dy by dx, and once you know the graph, once you find out the slope, so from the so you see use this you have a slope value. Slope is r square l square upon g l0 a square. So 1 upon a square you can find out from the intercept. So you go, because you see this is the intercept you can calculate. Once you plot the graph, you find this intercept. If you know the intercept, you put the value of the intercept as per the scale and find out 1 upon a square. And once you find 1 upon a square, because this is you can calculate a square, and you know once you know a square, you can put 1 upon a square here, right? And the slope is known to you. You calculate the slope, dy by delta y by delta x, that is the slope. So you put the value of slope here. So when you put the value of slope here, and you know the value of a square, you calculate the value of a square here. So you can calculate the value of r square. And once you know the value of r square, you take the square root, you will find out the coefficient of damping or a damping coefficient. So this is your objective of the experiment, that to find out the resonance length and to find out damping coefficient of, of right. Of, so this experiment is designed to find out a damping coefficient R and to study the resonance length L0. So I have explained the entire experiment. You see, I have already mentioned the results here. The results are taken. You see, this type of 20 oscillations are there. So you can take these oscillations. You see here, this experiment. I take the two observations. I'm sorry, I took the two observations. You find out the periodic time because I have taken for 20 oscillations. So you first find the periodic time. Then you find out the resonance length using this formula. So this is the first part you have to do. Estimate the resonance length, and then you perform the experiment, actual experiment. You take different length of both the on both the sides of the L0. That is length less than L0, length greater than L0. Take at least 6 to 7 observation. Find out the maximum amplitude. You see, I have given the 5 observations. So you do these calculations because you will be given an assignment to do this, perform this experiment. Since you cannot go to the laboratory, you cannot take the results. We are providing you the results. So using this result, You plot the graph and find out the resonance length L0. And once you find the resonance length L0, you prepare the observation table for part 3. You see, I have taken the observations for different masses. I have calculated the maximum amplitude. Now you have to do the calculations. You perform these calculations, plot the graph of 1 upon a square versus 1 upon m square, find out the intercept, find out the slope, find out 1 upon a square, find a, and you find out the coefficient of damping, and you can complete this experiment. So this will be your assignment. You have to perform. You have to sorry. You have to perform the calculations of these experiments and try to understand the physics of resonance. We have studied the mechanical resonance, and I gave you the concept of this experiment. The physics which we have used is the periodic time of the simple pendulum is equal when it is equal to the periodic time of the bar pendulum, then the resonance occurs, and at that resonance amplitude of a simple pendulum is maximum, and we use this principle, and we have studied the compound pendulum. You see, in addition to this exercise, I am also giving you another exercise which you can perform at your home. You see, there will be an assignment number in the same assignment. In the assignment, there will be two exercises. The first exercise is to perform the calculations of this experiment and prepare your journal. And there is another experiment which I'm proposing to find out the radius of gyration of Zara. The Zara is basically a kitchen instrument which you are using to prepare puris. So that instructions are given. I have prepared a instruction how to find out a radius of gyration of Zara, right? And the detail is given in the assignment. So this assignment is optional. In fact, there is one assignment, but there are two parts. Part one, you have to perform this exercise. Part two, there is an exercise which is an innovative experiment which you can perform at your home to find out radius of gyration of the Zara. Which these are the Zara. This is basically a kitchen device which your mother is using to prepare the garam puris. You know that Zara, you can find out the radius of gyration. So that attachment is given to you. So you perform that experiment at your home. You can perform this experiment. You don't require any devices. Only you require basically a stopwatch and some other devices which is available at your home. Perform that experiment, take the observations, and you can compare your results and find out the radius of gyration of your Zara, and you can understand the physics of radius of gyration of pendulums also. So with this, I stop here, and I hope that you will work out this exercise. Thank you very much for listening me. Thanks a lot.